We'll be looking at the central limit theorem here, which is going to be an important component as we move forward into hypothesis testing. So make sure you complete all of the exercises that go along with this section and have a firm understanding of this theorem and how it's going to apply to using the probability theory before we proceed into chapter 7 and especially into chapter 8. So the foundational principle of the central limit theorem is that the sampling distribution of sampling means approaches a normal distribution as the sample size increases. So let's take a look at what that means. And for that, we're going to run some demos. So you need to go to your Open Stats Crunch. So if you're opening up from the Blackboard side and you go to the Pearson for the homeworks, you go to your Pearson homepage and select Stats Crunch option there on your left-hand side. Then you need to be sure to select the option Data Sets from your textbook. Previously, we've been opening an empty set that we've been entering data in ourselves, but here we're going to open one of the data sets from your textbook. So we're going to open up data set 19, COLA weights and volumes. And once you have that open, you should be getting a data set with multiple columns of data. You need to go to this section labeled Applets on the left-hand side and select the option for sampling distributions. So pause the video here while you go through and get that open. You'll need to be going through running these applets yourself. They are not running on this PowerPoint. This only provides you the directions for completing them. So you need to have that open and be able to go back and forth between the two of them as we're completing this lecture. So pause the video, get that open, and then when you have that set, turn the video back on, and we'll proceed over to the next section together. All right, once you have that open, you should get something that looks like this as your dialog box. You want to be opening the data column of what represents Pepsi product diet weight. And I suggest that you title it the exact same thing down at the bottom. So I suggest you take that title of that column and enter that as the title for the applet that you're going to set up and run. We'll have a couple of these going, and so if you don't have them clearly labeled, they can become confusing. Once you've got that set, hit compute. You get something that looks like this. So here we can see in our top graph is the distribution for the full data set for the Pepsi product diet weight. If you look over here to the right, you can see the parameters for the full data set. So we have our mean, median, and our standard deviation for that particular data set. Moving down, we can see that we're looking at taking individual samples from that data set. So the number of data points the software is going to randomly pull from the data set above is specified in that box, currently with a 2 in it. And as it pulls each sample, the statistics for each sample are going to show up there below it for the mean, median, and standard deviation for each individual sample. Now what's going to happen is the software is going to pull a sample from the full data set above, plotting them on that middle graph. Then once it's plotted those data points, it's going to calculate the mean for that particular sample. Notice that's the sample mean. It's then going to take each of those and plot them in the graph on the bottom. That will become the sampling distribution of the sampling mean. So that very technical sounding term that was very long, we just talked about the sampling distribution of the sample means, and you were wondering what that was. That's what it is it's going to be this graph that we get here at the bottom. It is the distribution that occurs for the sample means, where we've taken a sample, computed a mean for it, and we plot that particular mean. Lastly, up at the top, we have the buttons that we use to specify the number of times that we want the process to repeat. So now that we're familiar with what we're working with here, let's do some exercises. So let's currently leave the sample size at 2 and select the option to run the process 5 times. Observe the pattern of the sample means. Pause the video here and complete that. Okay, now repeat this process another 5 times, and then finally select it for it to run it 1,000 times. Once you've completed that, note down your observations about the shape of the resulting distribution. How did the distribution change as you did 5 samples, 10 samples, and then the final one would be 1,010 samples. So write down your observations for that, and then pause the video while you go through this, and then once you've completed all of that, turn the video back on, and we'll move on to the next part together. Okay, now we're going to go through the exact same steps, only you want to change your sample size to 10. So changing your sample size from 2 to 10, and then again running it 5 times, another 5 times, and then 1,000 times, giving you the final end product would be 1,000 and 10 times. So pause the video, again, run those simulations and observe your results, and then jot those down so that we can come back and talk about them together. All right, the last time is running. We're going to run this for 30. Remember, 30 is the number for our n. We have to have an n that's greater than or equal to 30. So let's run this for 30, selecting the option to run a process 5 times, then another 5, and then 1,000. Again, noting your observations about this. So again, pause the video, go through this, run this applets, and then once you've completed that and jotted down your observations, turn the video back on, and we'll proceed to the next section together. Okay, so here we need to pull together what you've observed. So going through and looking, as the number of samples pulled from the original data set increased, what pattern did you observe about the shape of the distribution? So as we went from just having 5 samples to 10 samples to 1,010, what did you observe? So kind of organize your observations to answer this question. And then also, what happens when we had the size of the sample increased? So as we went from having 2 data points in our sample to 10 and then to 30, what did you observe there as well with the changing shape of the distribution? So pause, organize your thoughts, answer these 2 questions, get this in your notes so you'll be able to refer to it later. And then once you've got that organized, turn the video back on and we'll get back together on this. All right, you should have noticed that the sample, the number of samples pulled from the original data set increased. The distribution becomes more narrow and increasingly taller, right? So the sample mean that we wind up getting, it becomes closer and closer to being the same as the mean of the overall sampling distribution. Also, as the size of the sample increased, the mean of a single sample should have been much closer to the mean of the overall sampling distribution. So the mean, if you notice when you had the mean of 30 randomly selected data points from the population, that mean should have been very close to the final mean for the sampling distribution at the bottom of the page. If you didn't observe that, pause the video here, go back and rerun those applets again so you can reset them and rerun them, and then make sure you can come back and see the same pattern unfolding for yourself before you proceed any further. Okay, now we need to apply this. So the data set we previously worked with was a normal distribution. So although the distribution got more narrow and the mean started occurring more often, the shape remained normal. But what's really important about the central limit theorem here is the original population can have any distribution. It can be uniform, it can be skewed to the left, it can skew to the right. But the distribution of the sample means will approach normal when our n is greater than 30. So we're going to observe this now with a left skewed data set. So go through. It's set the same thing with the applets, but you're going to want to select the data column. This is going to be Coke regular weight. So this is the weight for a regular can of Coke. Okay? And again, we see the same setup over here on the right for our population mean, median, and standard deviation. And we're going to go through this same process as we did before. First is the sampling size of 2, running it 5 times, another 5 times, and then 1,000 times. And write down your observations about the resulting shape of the distribution. And then reset that and repeat again, going through the same steps for a sample size of 10 and a sample size of 30, each time jotting down your observations. Once you've completed, pause the video here while you go and complete all of those steps. And then once you've done them, let's get back together, turn the video back on, and we'll pull this all together. Okay, so what patterns did you observe? Again, is the number of samples pulled from the original data set increased. So as we went from 5 to 10 to 1,010, what change did you observe in the distribution? And similarly, what happened when we changed the size of the sample from 2 to 10 and then to 30? Should have observed very similar patterns. So our distribution should become more narrow and taller as the number of samples were pulled from the original data set. And also, we should have seen a similar thing as the size of the sample increased. But most importantly of all, for central limit theorem, indeed the key point is that the shape of the distribution itself approaches normal. So although the original distribution of the raw data is left skewed, as we pull and produce a distribution of the sampling means of that population, the shape of that distribution approaches normal. This is critical for underlying our ability to apply the normal distribution principles to a problem if we are solving for sample means, not a single individual, but sample means.